Alright, let's go. Number 10. The impossibly grown-up galaxies. Ivo Labe at the Swinburne University of Technology in Melbourne was doing what every observational astronomer does with a new telescope. He was building a source catalog. His team pointed the James Webb Space Telescope at a small patch of northern sky in the Kears Survey Field and started identifying the red, faint smudges that showed up on the earliest deep exposures. They expected the usual population of newborn galaxies from the first billion years. That was not what they got. The standard cosmological model, cold dark matter with a cosmological constant, or LING-CDM, makes a specific prediction about the first 500 million years. Dark matter halos assemble slowly, gas cools slowly inside them, stars form slowly on top of that. By 500 million years after the Big Bang, the most massive galaxies in the universe should hold roughly 10 billion solar masses of stars. No more. That is the ceiling the model has drawn for 2 decades. Labe's team found 6 galaxies above the ceiling. Several looked 10 times too massive. One candidate at redshift 7.5 appeared to hold more than 100 billion solar masses of stars, roughly the stellar mass of today's Milky Way, at a moment when the universe was 5% of its current age and should not have finished assembling anything comparable. The paper, titled A Population of Red Candidate Massive Galaxies, approximately 600 Mir after the Big Bang, appeared in Nature in February 2023. The lead author was Labe. The instrument was NERCam. The candidate redshifts ranged from 7.4 to 9.1. To build the observed stellar masses in that available time, the galaxies would need to convert almost every available baryon into stars, a star formation efficiency near 100%, at a time when the local universe averages closer to 10%, and no known feedback process allows the number to run that high. The rescue attempts came fast. Maybe the galaxies were dust-reddened active galactic nuclei, not stellar populations at all, but follow-up spectra from Erica Nelson at the University of Colorado and Bingji Wang at Penn State suggested that at least 3 of them really did contain massive, evolved stellar populations. Maybe the photometric redshifts were wrong, but spectroscopic follow-up confirmed several as genuinely early. Maybe the initial mass function was top-heavy, but no independent evidence for that has surfaced. Every fix creates a new problem. Every atom of oxygen in your blood was forged inside a stellar core. The timing of when those first stellar cores ignited sets the entire chain that eventually produced you. If early galaxies grew this aggressively, the clock on your own atomic history moves forward by hundreds of millions of years into a period the models describe as still dark. Did the first stars assemble so aggressively that the cosmological model has been wrong about the timing all along, and no one has noticed for 20 years? The problem got worse when a second independent JWST program tried to shrink Labe's galaxies back down. Number 9. The Red Monsters. Mengyuan Shao, a postdoctoral researcher at the University of Geneva, was leading analysis for a JWST survey called FRESCO, the first Reionization epoch spectroscopically complete observations. The goal was ordinary: get clean spectra for early galaxies so that the mass estimates would no longer depend on broadband photometry alone. She was, in effect, trying to close the Labe debate by delivering the spectra Labe did not yet have. If the earlier result was a photometric mirage, an artifact of estimating stellar mass from a handful of color measurements, then getting real, resolved spectra should shrink the anomalous galaxies back down. That was the assumption every skeptic in the field carried into the FRESCO data release. Spectra are trusted. Photometry is a guess. Spectra were supposed to fix everything. They didn't. 3 of the galaxies got bigger. The paper, Accelerated Formation of Ultramassive Galaxies in the First Billion Years, appeared in Nature in December 2024. Shao's team spectroscopically confirmed 3 galaxies at redshifts between 5 and 9, with stellar masses near 100 billion solar masses. That is roughly Milky Way mass, assembled inside the first billion years. Following the standard LCDM efficiency curve, these galaxies should not exist. The team calculated the required star formation efficiency at approximately double what any galaxy in the local universe achieves. The dust explanation was tested first. The galaxies look red because they are heavily attenuated by dust, so perhaps the old stellar population is illusory. Spectra ruled this out for at least the 3 confirmed cases. Gravitational lensing magnification could artificially inflate the flux, but the sightlines showed no massive foreground lenses. A top-heavy initial mass function was reconsidered once again. The objections that killed it after Lubbe still applied. Alternative dark matter models that predict earlier halo formation were floated, but no specific model reproduces the observed abundance without breaking constraints elsewhere in cosmology. The universe you live in has a founding chronology. That chronology tells you when heavy elements first entered stellar populations, when the first rocky planets could form, when the atoms that would eventually become your body first passed through a stellar core. Xiao's galaxies suggest that chronology needs to shift by several 100 million years in the direction of sooner. If the model is not just slightly wrong about the first billion years, but structurally wrong, what part of your body's origin story is still standing? That was the crisis of how much matter is where. The next crisis is over how fast the universe is stretching right now. Number 8. The Hubble Tension. Adam Rees, a Johns Hopkins astronomer who had already won a Nobel Prize for co-discovering dark energy, was refining a measurement he had spent his career on. His SH0ES team, supernovae, H0, for the equation of state, was recalibrating the distances to nearby Type 1a supernovae using Cepheid variable stars in the same host galaxies. It was routine maintenance on a number that most physicists had assumed was settled to within a percent. There is a value called the Hubble constant, H0, that quantifies how fast the universe is currently expanding. Two entirely independent methods should give the same answer. The first uses the cosmic microwave background, the light released 380,000 years after the Big Bang, and evolves the expansion forward through the CLPing-CDM equations. The Planck satellite collaboration published that number in 2018. It sits at 67.4 kilometers per second per megaparsec, with an uncertainty of about half a unit. Rees's team measured H0 locally. They got 73. The precise SH0ES value, published in the Astrophysical Journal Letters in 2022, is 73.04 SMON-MIS 1.04 kilometers per second per megaparsec. The Planck value is 67.4 SPLUSN more 0.5. The gap is roughly 8%. The statistical significance of the disagreement, assuming both measurements are unbiased, reached about 5 sigma. That is the conventional physics threshold for a discovery. In this case, the discovery is that two trusted measurements of the same quantity refuse to agree. Wendy Friedman at the University of Chicago introduced a third technique, the tip of the red giant branch, or TRGB, and got 69.8, splitting the difference and suggesting the Cepheid calibration might be biased. Rees pushed back with new JWST observations in 2023 that confirmed his Cepheid distances at the required precision. Early dark energy models, developed by Vivian Pollan and colleagues at Johns Hopkins, can partially close the gap by injecting an extra energy density before recombination, but they worsen fits to other CMB features. Modified gravity attempts have similar side effects. No proposal on the table is clean. The expansion rate sets the age of the universe, the size of the observable region, and the ultimate fate of every galaxy, including yours. An 8% discrepancy leaves the age of everything you can see uncertain by roughly 1 billion years in either direction. Your address in cosmic time carries an error bar wider than the age of Earth. If the faster expansion rate is correct, the universe is younger than the oldest known globular cluster stars. So which measurement is the physics of your reality actually built on? The disagreement about expansion is loud. The next anomaly is a place in the sky that should not be there at all. Number 7. The Eridanus Cold Spot. The team analyzing WMAP satellite data in the early 2000s was doing statistical hygiene. They were combing the cosmic microwave background, the thermal remnant of the recombination era, for regions that deviated from the mean temperature by more than random chance predicted. Patrick Vilva and collaborators at the Universidad de Cantabria in Spain ran a spherical wavelet analysis to identify unusual patches. Most anomalies vanish under a second look. One did not. The CMB should be almost perfectly uniform, with tiny temperature fluctuations of about 1 part in 100,000, distributed as Gaussian noise across the whole sky. The largest cold or hot spots predicted by LCDM should have angular sizes of roughly a degree and temperature differences of tens of microkelvin. That is what the theory demands. That is what nearly every patch of the CMB delivers. In the constellation Eridanus, they found a cold region 5 degrees across, with a central deficit of about 70 microkelvin below the mean. Vilva and colleagues published the finding in the Astrophysical Journal in 2004. The spot is centered near right ascension 03H15m and declination -19 degrees. Its angular size is roughly 10 times larger than the largest cold spot IL-CDM comfortably predicts. The probability of a fluctuation this extreme arising by chance, in a purely Gaussian sky, has been estimated at less than 2% depending on the statistical method used. The leading explanation was that a giant void, a nearly empty region of the intergalactic medium, sat along the line of sight, and CMB photons crossing it lost energy through the integrated Sachs-Wolf effect. Lawrence Rudnick at the University of Minnesota reported evidence for such a supervoid in 2007. Later surveys, including work by Istvan Sapudi at the University of Hawaii in 2015, largely confirmed the presence of a void. But independent calculations by other teams showed the void is not deep enough to account for the full temperature deficit. Neil Turok's group has proposed a cosmic texture, a topological relic left over from a symmetry-breaking phase transition in the early universe. No such texture has ever been independently observed. A void this large, if real, means the local patch of universe you occupy is less dense than average, which changes how you calculate everything from local expansion rate to the ages of nearby galaxies. Your entire cosmic neighborhood may be sitting inside a much larger underdensity than the model expects the universe to contain. If the Eridanus cold spot is neither a fluke nor a foreground, what class of object leaves that kind of imprint on the sky and has never been seen anywhere else? That was a place in the sky. The next anomaly is a direction the sky itself seems to prefer. Number 6. The axis of evil. Kate Land and João Magajo, both at Imperial College London, were investigating whether the largest scale patterns in the CMB behaved as randomly as IL-CDM required. Magajo, a theorist who had built his career questioning fundamental symmetries in physics, ran a battery of statistical tests on WMAP's low multiple moments, the temperature patterns that vary across the largest angular scales on the sky. They were looking for confirmation of statistical isotropy. They found alignments that had no right to be there. The universe is supposed to have no preferred direction. This is the cosmological principle, the foundational assumption embedded in every equation used to describe the large-scale structure of everything. The quadrupole and octupole moments of the CMB, which describe temperature variation across the sky at scales of 90 degrees and 45 degrees, should be oriented randomly with respect to each other, and with respect to the local frame of the solar system. They line up, and they line up with us. Land and Magajo published Examination of Evidence for a Preferred Axis in the Cosmic Radiation and Isotropy in Physical Review Letters in 2005. They named the alignment the axis of evil. The quadrupole and octupole axes are aligned with each other to within about 10 degrees. Both are aligned with the ecliptic, the plane of Earth's orbit around the Sun, and with the equinoxes. The chance probability of that combined alignment arising randomly has been estimated at less than 1% in multiple analyses. The obvious explanation is contamination. Perhaps the CMB analysis was not properly subtracting emission from the solar system, or the plane of the Milky Way. Planck satellite data, released in 2013 and 2018 with substantially better foreground modeling, largely reproduced the alignment. A statistical fluke is still formally possible, but the probability keeps refusing to grow with better data. Some theorists have proposed a preferred direction baked in at inflation that violates the cosmological principle, which is not a small price to pay. Others have suggested unusual global topologies for the universe. No proposal has produced independent confirmation. If a direction is real, the equations describing the geometry of your reality, every calculation of distance, expansion, and structure formation, are being solved with an assumption they don't obey. The universe is being modeled as symmetric. Your universe may not be. If the CMB really does align with the ecliptic, does that mean the local solar system is special, or that our data still hides a systematic no one has managed to find? That was symmetry breaking. The next anomaly is something more basic. For years, half the ordinary matter in the universe was missing. Number 5. The Missing Baryons. Masataka Fukugita, at the University of Tokyo and P. James E. Peebles at Princeton were doing bookkeeping. In a 2004 paper in the Astrophysical Journal, they took the tightly constrained total baryon density from Big Bang nucleosynthesis and the CMB, and they added up every observed reservoir, stars in every galaxy, interstellar gas, X-ray gas in clusters, the intracluster medium, everything astronomers had ever catalogued. The sum came up short. They wrote the shortfall down as an accounting problem and asked where the missing atoms had gone. Big Bang nucleosynthesis, the sequence of nuclear reactions during the first 20 minutes of the universe, predicts the total density of baryons, meaning protons and neutrons, with unusual precision. The CMB provides an independent measurement of the same quantity. Both agree. Baryons make up about 4.9% of the total energy density of the universe. Every hydrogen atom, every carbon nucleus in your body, is part of that budget. When you count what telescopes can actually see, you find about half. Fukugita and Peebles pegged the observed fraction at roughly 60% of the predicted total, depending on assumptions. Later inventories put the deficit closer to 50%. The missing component was theorized to be a diffuse, hot, ionized plasma between galaxies, the warm-hot intergalactic medium, or WIM, with temperatures spanning 100,000 to 10 million Kelvin, almost invisible in every waveband, fully predicted by the theory. For 15 years the WIM stayed mostly hypothetical. X-ray absorption lines searches by Fabrizio Nicastro's group at the Osservatorio Astronomico di Roma detected candidate lines, then lost them, then found them again, never at high enough significance to close the case alone. Ultraviolet absorption searches with the Hubble Space Telescope's Cosmic Origins spectrograph, led in part by J. Michael Schull at the University of Colorado, recovered part of the deficit, but not all of it. Then in 2020, Jean-Pierre Macquart and collaborators used fast radio burst dispersion measures, the way an intervening plasma smears out an FRB signal across frequencies, to weigh the intergalactic medium along 5 sightlines. Their Nature paper reported that the missing baryons had been located, mostly. Your body contains atoms that spent most of the last 13 billion years suspended in an ionized fog between galaxies. Confirming this is not just an accounting fix, it verifies the entire chain that takes primordial hydrogen and eventually deposits it into your bloodstream. The FRB result closed most of the gap, but not all of it. Where is the remaining fraction, and why has a decade of dedicated searches still not nailed it down? That anomaly is closer to solved than most on this list. The next one is not. Number 4. The Lithium Problem. François and Monique Speet, a husband and wife team at the Paris Observatory, were surveying old, metal-poor stars in the halo of the Milky Way in 1982. Their instrument was measuring elemental abundances in the atmospheres of stars so ancient they were expected to preserve a near-primordial composition, largely unaltered by later stellar processing. They expected lithium abundance to scatter widely with stellar mass and temperature. They found the opposite, a strange, quiet plateau. Big Bang nucleosynthesis is a precisely predictive theory. Given the baryon density measured independently by the CMB, it forecasts specific abundances of hydrogen, helium-4, deuterium, and lithium-7. For deuterium and helium-4, the predictions match observations to within a few percent. For lithium-7, the standard model predicts a primordial ratio of Li7 to hydrogen of about 4.7 × 10⁻1 no. The old stars showed roughly 1.6 × 10⁻1 no, about 3 times less. The Spites published their result in Astronomy and Astrophysics in 1982. The flat abundance across their sample became known as the Spite Plateau, evidence that these stars had never significantly processed their surface lithium, and so preserved a primordial signature. Brian Fields at the University of Illinois and others confirmed and sharpened the discrepancy across 4 decades of follow-up. The mismatch, at a factor of roughly 3, sits at about 4 to 5 sigma statistical significance and has not shrunk with better data. The most popular explanation is that lithium is destroyed inside the stars themselves, sinking beneath the convection zone through atomic diffusion. Andreas Korn at Uppsala University measured lithium abundances at multiple depths in stars in the globular cluster NGC 6397 in a Nature paper in 2006 and found evidence for exactly this depletion. but the effect he measured was too weak to account for the full discrepancy across every sample. Alternative solutions have looked at revising nuclear reaction rates in BBN. Those have been remeasured in laboratory experiments and remain firm. Non-standard BBN scenarios involving decaying supersymmetric particles have been proposed by Karsten Yadamczyk at the University of Montpellier. None have been confirmed by particle physics experiments at the LHC or elsewhere. The abundances of the lightest elements are what tie your body's hydrogen budget directly to the first 3 minutes of the universe. Every other prediction from that era holds. The one that fails by a factor of 3, and has been failing for 40 years without a resolution the field can agree on. If the standard model of Big Bang nucleosynthesis is right on every element except lithium, is the error in the stars, in the nuclear physics, or in the model of the first 3 minutes itself? That anomaly is old and unresolved. The next one, the timing of when the universe first went transparent, is being actively rewritten this decade. Number 3. The Reionization timeline. Sarah Bosman, then at the Max Planck Institute for Astronomy, was remeasuring quasar sightlines. She was using bright, distant quasars as flashlights, shining backward through the intergalactic medium. The specific wavelengths of light absorbed along the path encode how much neutral hydrogen was present at each redshift. The goal was to sharpen the endpoint of the epoch of reionization, the era when neutral hydrogen was ionized by the first sources of ultraviolet light. Simultaneously, JWST teams were beginning to count the ionizing photons produced by the earliest galaxies. The standard picture placed reionization ending around redshift 6, about 1 billion years after the Big Bang. Small, faint galaxies were assumed to produce most of the ionizing UV. The transition was thought to be relatively rapid. All of these were educated guesses, constrained mostly by CMB polarization data from Planck and a small handful of quasar sightlines from earlier surveys. The timeline broke in both directions. Bosman's 2022 analysis of the Lyman alpha forest, using 67 quasar spectra, showed neutral hydrogen persisting until roughly redshift 5.3, meaning reionization ended later than the standard picture assumed. Meanwhile, JWST spectra, reported by Hakim Atek at the Institut d'Astrophysique de Paris in a 2024 Nature paper, found that small galaxies at redshift 6 to 8 produced far more ionizing photons per unit stellar mass than models had ever assumed, meaning the sources doing the ionizing were in place earlier. The universe started ionizing sooner and finished later. The middle of the process now spans several 100 million years more than the previous model reproduces. One resolution attempt is to raise the escape fraction of ionizing photons, the fraction that escape their host galaxies, rather than being absorbed inside, but the required values conflict with escape fractions measured directly in nearby analog galaxies. Another is to invoke a population of active galactic nuclei, quietly doing much of the ionizing. JWST has found more early AGN than expected, but not nearly enough to fill the gap alone. A third is to modify the nil-CDM structure formation timeline, which brings back the massive galaxy problem from number 10. Every fix pulls another string. The moment the universe became transparent to visible light is the boundary condition for everything that follows. The first galaxies you can see, the light that eventually reaches your telescope, your eye. A messier and longer reionization means the boundary itself is smeared out in a way no current model reproduces from first principles. If the universe's first light escaped earlier and lingered longer than expected, what were the sources, and why can't the standard model account for either end of the timeline it once claimed to describe? That anomaly is about what turned the lights on. The next one is about the moment before there were any lights at all. Number 2. The missing primordial gravitational waves. The BICEP-2 team, running an experiment at the Amundsen-Scott South Pole Station, was searching for a specific polarization pattern in the CMB called B-modes. B-mode polarization on large angular scales would be the smoking gun signature of cosmic inflation, the theorized exponential expansion in the first fraction of a second after the Big Bang. In March 2014, John Kovac at Harvard and collaborators held a press conference announcing a detection. The paper appeared in Physical Review letters. Nobel Prize speculation began within the hour. Inflation makes a specific, testable prediction. The rapid expansion should have produced primordial gravitational waves, which imprint a curling polarization pattern on the CMB. The ratio of these tensor perturbations to the ordinary density perturbations, called R, is set by the energy scale at which inflation occurred. Popular models, chaotic inflation, and the family of large field models associated with theorists like André Linde predicted R somewhere between roughly 0.01 and 0.1. Well within the detectable range, in other words. The BICEP 2 signal turned out to be mostly dust. Within months, joint analysis with the Planck satellite showed that galactic dust polarization contaminated the BICEP 2 patch far more heavily than the original team had estimated. The claimed detection was quietly retracted. The BICEP/Keck collaboration then combined data through 2018 and, in a 2021 Physical Review Letters paper led by Pa Aide and colleagues, set the tightest upper limit to date, R less than 0.036, at 95% confidence. Not a detection, a constraint. The constraint has consequences. Chaotic inflation models with a simple quadratic potential, the ones Linde built much of his career around, are now ruled out. Higgs inflation models are heavily constrained. Small field inflation models survive, but they are harder to motivate from particle physics arguments. Some cosmologists, including Paul Steinhardt at Princeton, have argued the accumulating null result should push the field to abandon inflation entirely in favor of cyclic or bouncing universe alternatives. Other theorists insist inflation is still the best framework and the signal simply sits below current sensitivity. Both camps have been talking past each other for a decade, with no resolution in sight. The reason your universe appears smooth, flat, and roughly the same in every direction is supposed to be inflation. The prediction that would have confirmed it directly has now been searched for by 3 generations of experiments and not found. The theory that explains the shape of everything you can see rests on evidence that keeps failing to appear. If primordial gravitational waves stay unseen as the next generation experiment, LIGHTBIRD, comes online in the 2030s, does inflation survive as physics, or slip into the category of an idea that cannot be tested? That is the state of 9 anomalies, each of which could still be measurement error. Number 1 is what happens if they are not. Number 1, the moment the model breaks. Cosmologists work by triangulation. When a single measurement disagrees with theory, they look for systematics. When 2 independent measurements disagree, they take it more seriously. When 5 or 6 independent probes all disagree in the same direction, they begin writing new theory. Across 2024 and 2025, several senior cosmologists, including Adam Rees, Wendy Friedman, and members of the JWST early universe groups, began publicly acknowledging that the accumulation of tensions no longer looks like coincidence. LUS-DM has been the working model of cosmology for a quarter century. It has 6 free parameters. With those 6 numbers, it reproduces the CMB anisotropies, the large-scale distribution of galaxies, the acceleration of cosmic expansion, and the abundances of light elements mostly. The model has always been understood as effective, not final. The question was where it would first fail. The current answer appears to be everywhere, a little bit, all at once. Every anomaly on this list, if genuine, points the same way. Structure formed earlier than the model allows. Expansion behaved differently in different eras. Symmetries were broken at the largest scales. The framework is quietly wrong. The Hubble tension alone stands at roughly 5 sigma. The JWST massive galaxy tension sits at 3 to 4 sigma depending on the sample. The lithium discrepancy is at 4 to 5 sigma. The axis of evil alignment is at roughly 2 to 3 sigma. Any one of these could be traced back to instrumental systematics, all of them being systematic simultaneously, with no unifying source of error found despite decades of dedicated search, is itself starting to look statistically unlikely. Proposed replacements have started to accumulate. Primordial black hole dark matter, revived in recent papers by Bernard Carr at Queen Mary University of London and others, could seed early massive galaxies and modify structure formation timelines. Interacting dark energy models, tested extensively by Eleonora Di Valentino at the University of Sheffield, can partially close the Hubble tension. Modified gravity extensions, men-distended proposals like MOGE from John Moffat at the Perimeter Institute, can address large-scale anomalies but strain small-scale galactic constraints. Early dark energy resurfaces every year with a new variant. No single alternative fits all the data. The picture of the universe you have inherited, inflation, dark matter, dark energy, structure formation, 13.8 billion years of tidy history, is a model. Models are approximations. The one you were taught in school is approaching the edge of the regime where it works, and it is doing so in more than one direction at once. If the standard model of cosmology fails, and no candidate replacement covers the full dataset, what does it actually mean to say we understand the universe your body currently lives in? Every anomaly on this list sits inside our best-tested theories, not outside them. The universe is not confused. We are. 9 independent tensions have piled up at the foundations of cosmology, and the 10th, the possibility that they are all real, all at once, is the one no working model resolves. The framework you were taught as settled is a hypothesis that is quietly asking to be replaced, and the field is only just beginning to admit it out loud. If you want to see more videos like this, click the video on screen now.